Thanks a lot, and yeah, good afternoon, everybody. So I'm Richard Saxton from ESAC, and I'd just like to talk to you about the X-ray selected TDEs, what we know about TDEs from X-rays, and to talk a little bit about the models and the modelling of the disk in particular that we can get from these observations. So very briefly, historically, then we got into TDEs via the XMM SLU survey. We made a big catalogue in 2006, and then looked for transient sources. We found some interesting sources and a few galaxies which didn't appear to be AGN, which were massively variable. Looked in the literature, found out there's these things called tidal disruption events. Fantastic. So we'll start from there, and got in touch with Stephanie Camossa, who was incredibly helpful to us and was a great collaborator for many years. Telling us what had gone on in Rosetta and bringing it into the XMM SLU survey. So in those days, we had this canonical view that a TDE had to have a T to the minus 5/3 decay, it had to have a soft X-ray spectrum, and it had to have a quiescent galaxy optical spectrum, otherwise it wasn't a TDE. So if it walks like a TDE, talks like a TDE, and all that sort of thing, then it is a TDE. And this is an extremely bad idea, actually, because we ended up missing very interesting sources. So GSN 069 we discovered in 2010, massive soft X-ray flare, but it was a CFERT2, therefore it can't be a TDE, it's an AGN, obviously, with some sort of accretion disk transition, blah, blah, blah. However, a few years later, we kept on monitoring it, and in 2019, it did this QPE stuff, which is quite famous now. And then going back from there, then we know that this, or we think now that this is a TDE which happened, you know, like 20 years ago or so. So the point being that when you're doing your rates and everything, then you have to make sure that you include all of the TDEs, all of the parameter space, because almost everything is possible. Okay, so non-canonical light curves. What we find in several, if not all of these TDEs, is that we get this plateau which comes on. And we tend to find it in X-rays. You don't tend to find it at the same time as the optical peak. You tend to find it in the plateau stage. In this one on the left, then the plateau goes on for like 100 days and then decays away over the next 1,000 or so. And in this new one, which I'm going to spend a lot of time talking about, then again, the plateau is 100 days-ish, and it decays incredibly rapidly over a couple of 100 days. Either in the X-rays or the bolometric, it's the same sort of thing. And in this one, then in both these, you see that the optical plateau lasts for longer than the X-ray plateau. And this has got to be telling us something. Okay, so what about the plateau models? Then we know we have a disk, and there's two ways of looking at it. Then there's the nice model from Wen in 2020, where basically they're saying in this slim disk model, then the matter falling back is super Eddington, and you're getting a level flat light curve because you can't have more than Eddington, and then until you go below Eddington, it doesn't fall off, then it falls off rapidly. We don't think that is the case in our TDEs, because we think they're accreting sub-Eddington. So more like it's the model where you have a disk which is like acting as a reservoir for material fast, and it keeps more material faster than it actually comes in. So, okay, anyway, so we have a disk. This is an important thing. So XMM 1404, we have the light curve, but what's even more interesting about it is that we have a very interesting spectral behavior. So in the very early days when we slewed over it at first, then we found it had a thermal spectrum of about 80 EV, pure thermal. Very rapidly, like within 10 days or so, it started to develop a hard tail. And by 150 days, then this was the completely dominant spectral component in the X-rays was the hard component. So if you take all of the observations and then you fit a Comptonized thermal black body, then you see that over like 10 days, then the Compton corona has developed. Over 20 days, it's pretty much already there. And so it's like incredibly fast, basically, in terms of producing a corona. This is just one example, and of course, since then, there have been quite a lot of other examples. This is a very nice one from Yao and collaborators in 22, 21 HB, which is an amazing source, and this changed from the thermal to the hard state in 200 days, and then incredibly rapidly from the hard back to the soft excess state in 3 days. What do we mean by these states, so that we're all on the same page? We have 3 states effectively in the X-rays, or 3 spectral components. There's the thermal disk, from the disk. There's the soft excess, which is from a warm corona, we believe, which with electrons of around a few keV. And then the famous power law, the AGM power law, which is from much hotter electrons, which are in some sort of state very close to the black hole, but we're not quite sure what it is yet. Okay, and so a few more of these state-changing TDEs. Thomas has got this one from 2018, YHK, which changes state on timescales of 100 days or so. And also, interestingly, it did it once and then it did it again to show that it's most likely a partial TDE, which came back. We have this beautiful one, 2019 AVD, almost everybody's favourite TDE apparently, which had a soft to hard transition in 40 days, strangely enough going downwards rather than going upwards. And then this incredible TDE, which has got to be the best TDE in the world, which is this super multiple partial TDE, which has got 5 cycles now, and changes its hardness depending on contributions from the warm and the hard coronas, hot coronas, but like cyclically, so that's incredible. So partial TDEs are amazing for looking at state changes. Okay, so how do we interpret XML 1404 now? So first of all, when we stewed over it, it formed this accretion disk, which we saw, just an accretion disk. Started to build a warm corona, did this very quickly. The accretion disk cools over time, and so the thermal X-rays fall away a bit, but the corona stays there. So the corona stays there, upscattering the UV and EUV photons still. The corona starts to fall off because you're losing energy as the accretion rate goes down, and you end up with just the optical disk, and eventually this one goes away as well. So over like 1, 2, 3 years, the whole system is dead. And now this is fast on time compared with other TDEs. So there's that little point down there with the ring around it. So we think this is probably a partial TDE, and there's not been that much material which has gone into the disk basically. So it's like drained away very quickly, or more quickly than usual. Okay, so just to look at other examples of historical TDEs, there's this IC3599, which is a massive soft X-ray flare from Rosetta, which did it again in 2010. And we assumed, because it was an AGN, then we assumed we read this paper about the fact that this was AGN state transition variability, nothing to do with TDEs. Competing group, Campana et al. Said at the time, this is a partial TDE, and we laughed at them. Shouldn't have done that, because I think, having seen what's going on at the moment and all the other partial TDEs, then they were probably right, actually. And this is just a very long 20-year partial TDE. And the Rosetta's got another one as well, which I'm not going to bother showing here. But okay, just to say very briefly, this is a complicating factor for the interpreting binary black holes in terms of the light curve, where the second black hole comes in and takes away disrupts the accretion. There may be other ways of doing it, but just to interpret the light curve as binary black hole is difficult, I think, because of partial TDEs. Okay. Now, what's really interesting, I think, now that we've got so many TDEs and so many spectral states, is to start plotting things and say, when we look at the accretion rate, the Eddington rate, what do we see in terms of the spectral state? Because, you know, from AGN, then there's all this stuff about when you get down to 0.1 Eddington, then it changes state and all that stuff. Well, with TDEs, of course, we can see this in real time. We don't have to have huge samples to do this. So here's a plot of the Eddington rate against the time since the optical peak, down there. And the little symbols are coded so that if it's an open symbol, then it's in the thermal state. If it's kind of a grey symbol, then it's in the soft excess state. And if it's a solid black symbol, then it's in dominated by the power law. So you can see from here it's a bit of a mess. It's not clear as such. When you look at the actual values, then the thermal state can, from what we've seen, go from accretion rate of 0.01 to 1. The hard state from 0.01-ish to 0.1. And the soft X-ray state from almost nothing up to 0.1 or 0.2 or stuff. So, I mean, the 1404, we happened to find it when it was at around 0.1, and I think we were just looking that it was kind of in the transition state, and it transited just as we got there. But basically, I mean, okay, there's some scatter on this, but what we're not seeing is you get down to a certain level and it changes state, then you get down to another level and it changes state again. It's a mix. And what's interesting, I think, is to find out why it's a mix and what other factors apart from the accretion state are involved here. Okay, so quickly, the thermal state is amazing. I don't think we appreciate how incredible this is, because as far as I know, there are no AGNs which are persistently accreting, which are in the thermal state. They've all got hard coronas. You may tell me I'm wrong, I don't know, but as far as I know, out of 300,000 XMM AGN, there are 5 or 6 which are thermal and not obviously TDEs, and quite probably they're TDEs as well. Okay, so all right, so I was just saying, like, when you look at AGN studies which are not XMM based, which are not X-ray based, then again you kind of always find an X-ray corona. So it's extremely difficult, if not impossible, to find a thermal AGN. Has to be a reason for this. Possibly it's the time it takes to accrete, or the way that the material falls in. Don't know. So quickly, what can we get from thermal? Thermal spectra are very useful because you can use them to find the black hole mass, caveat the inclination angle and caveat the spin, but to some extent anyway. And they're also great because you can see the outflows probably clearer in thermal TDEs than you can in the AGN, because in the AGN then you've got the so many other different features going on. Right, so so as I was saying before, what is it which really makes the hard corona switch on? I think this is like a massively interesting question which only we TDE people are going to be able to solve. We haven't solved it yet, but we will do. So what are the possibilities? I mean, one crazy thing is that when the optical sample from Wulo, you look at the X-rays from the optical sample, and only 4 out of 17 develop a corona so far. The XMM SLU sample, 10 out of 12 have got a corona. Possibly this is just selection effects and biases, but it's intriguing. And so if we look at the whole thing, you see that sources with the same age and with the same accretion rate, some have coronas, some don't have coronas. So there must be extra characteristics, parameters of the system which are involved. It's not black hole mass, because if you plot it as black hole mass, then you see the hard corona from 10 to the 6 to 10 to the 8, basically. And we know from AGN and black hole binaries that you get the hard corona in all of the states. The accretion rate has obviously got something to do with it, but it's not the limiting factor either. Is it the time for, people talk about the time for the MRI effect to wind up, so you get enough magnetic fields. Something to do with that as well, possibly, in that we don't see the hard state until a couple of 100 days in most cases. But obviously that's not the definitive thing either. Is it the black hole spin? Could be. Is it the onset of the jet, which we'll come to? And is it, as some people have mentioned, the fact that you have a magnetic star in some cases and a non-magnetic star in other cases? Or could it be that the black hole is initially charged up as well? Okay, so, I mean, if we can solve this, it would be really, really nice, because it can help to decide where the corona comes from. Help to decide where the corona comes from, because there are models, of course, that it's the base of a jet, and others that it's a more extended corona, and there's all sorts of reverberation studies which have which have put evidence for both of these. quite a lot into the base of the jet in terms of looking at large samples of AGN and correlating various principles. That's, you know, very nice, but it would be really, really nice if with TDEs we can watch watch the actual hard corona form in the X-rays, like pepper it with radio observations and see if we can see anything with one which does form and one where it doesn't form, and see if there's any differences. I mean, this could be quite expensive because you don't know which one's going to form a hard corona or not, I know. But it's a possibility. And so this Wang et al. Paper from this year kind of did that. I think it's the closest that's come at the moment. And they were claiming that when they saw the hard state, then a radio observation just a little bit later was showing evidence for a compact jet. I think we need more evidence than this, but it's certainly going in the right direction. So, I mean, it would be nice if we could do this a little bit systematically in the radio. Or possibly, I mean, as we saw yesterday, it's difficult to know where the radio is coming from, and it may be you don't see anything at the time of the hard corona, you don't see anything in the radio, but 3 years later you do. And so there could be a difference between the samples which have got hardened coronas and don't have in terms of their long-time radio properties. Okay, so that's it. So summary, I think we have the only possibility of studying the thermal state in supermassive black holes, I think, which is good. You don't build to build the hard state corona, you need several different factors, and I think we're still working out what they are, and it would be nice to find out. How long does it take to build the corona? What are the factors involved in that? We can find out with bigger samples, maybe. Partial TDEs are fantastic for studying transitions, and yeah, okay, so there's some ambiguity between binary black hole-like curves and partial TDEs. So thanks very much, and I'd just like to advertise conference, which will be coming up next year, I hope. No. Thank you.
Okay, any questions?
Hi, great talk. Just to mention that the three corona-forming TDs in our paper, for the three we have radio observations and none of those shows detections.
Oh, right.
Yeah, so I mean we don't have perfect cadence, but we have at least one observation, all of them. Radio observation, there's no detections.
And that observations, that's close to when it turned on, is it?
I don't have the numbers in my head, but like we observe all of them with radios. I mean, Kate observed, and there's no detections for these three. Yeah.
Okay.
Just quickly, going back to your huge sample of TDEs with the edited ratio and time scale.
Yeah.
I'm not going to play again. Yeah. You mentioned the various issues selecting X-ray TDEs at the start, but what went into selecting these?
What is it, what?
What went into selecting these ones?
Well, when it's selecting these, well, okay, so most of these are optical ones, actually.
Okay.
So they're kind of a few of the standard ones which we picked up from the X-Men SLU survey, which all the standard characteristics, I think, apart from the ones which we're not supposed to, which should be ignoring, then you know, they've stood the test of time, basically, and they look like TDEs even now.
Yeah, I have a question on the same plot. Okay, it's a very complicated plot. So you notice that in the upper part, above 10% Eddington, then they're all soft, right?
Most are soft, yeah. That's
Another thing that I noticed is that beyond 300 days, there are nothing, right? There may be a couple of things, but most of them are restricted within the first year. So it looks like there's something, and also for some other individual cases that you show that there's some rapid drops in X-ray, 100 days, maybe some of them 200 days. And that time is also the same as when in the jetted TDEs when the jets shut off. So, many people know it's 1644, 80 CMC. Mm-hmm. So I would make a wild guess that it's the jet that is perhaps related to some of these hard states, the power law. I mean, it's a wild guess, nobody knows in detail, that gets rid of all those beyond 300 days.
Yeah, so the jet shutting off in 1644, for example, is when it's supposedly when it drops below Eddington, right?
Yeah, it could also be that's just the time scale for this to drop below Eddington.
Yeah. Okay, so obviously I skipped over quite a lot, but the big problem with this is the bolometric correction factor, of course. So you're usually extrapolating from the X-rays or the X-rays plus the optical. And that's a difficult extrapolation, and everybody does it differently. Most of these I took from the literature.
So you mean your Eddington limit is not really well measured? Well, Eddington factor is not really well measured.
In any individual source, no. But I think if you look at the whole conglomerate of them, then because you can see patterns, then it's obviously not completely wrong.
But anyway, we can discuss this further. Okay, thank you.
Awesome talk. So anecdotally, from looking at the XMM light curves of a bunch of TDEs, they show a wide range of different variability patterns on different time scales. Some of them are basically flat over your tens of kilosecond observations. Yeah. Some of them show all sorts of stochastic variability. Have you looked much into whether that correlates with the presence of different spectral components or any of those properties in your list, or whether you can characterize the variability in any way? Yeah, no, that's a very good point, in fact, and I haven't, but a lot of other people have done that, of course, yeah. And when these change state, then that's one of the very good supporting pieces of evidence that in the hard state, of course, the variability is faster, basically, because it's a smaller region. In the thermal state, you get very little variability, which also correlates with what you see in black hole binaries, and the same reason, right? Yeah, no, you're dead right. That's a helpful diagnostic. Yeah.
Hi, Megan Newsom. Maybe you can help me understand connecting this talk to the previous one, so I can understand how much these should be reprocessed to possibly explain why we don't see them in optical events, if at all, especially the corona state that you're so curious about.
Yeah, well, okay, so most of these are optical TDEs as well, right?
Yeah. I guess if you don't see the corona, though, why could that be explained by the reprocessing scenario in the larger photosphere?
Haven't thought about it. I don't immediately see why. So the reprocessing, of course, takes away everything from the X-rays. Basically, we don't see anything. If the unification model is right, then and it's only which way we look at it, and all of the TDEs are the same, then whether you're looking that way or that way, it shouldn't make any difference whether it forms a corona or not. So I'm assuming not. But we haven't. I haven't correlated, for example, with the total optical luminosity to see if that's got anything to do with it. No. Thanks.
So I had a quick question. So you're saying that partial TDEs are great for seeing these state transitions, but I would assume that in some of these systems you have some understanding of the total luminosity, and can you therefore turn that into an estimate of the amount of mass that's accreted, and thereby see if that's consistent with the interpretation? Yeah, sure.
Assuming you see everything, of course.
Yeah.
Quite often in the X-rays, then you miss the optical peak, which means you're missing significant fraction, but certainly true. So in 1404, for example, it's like 0.005. Forgetting about the optical peak, that's nothing. That's a very, very small amount, so it's quite possible. Yeah. Right. In GSN 069, then so far it's accreted 0.3. Yeah. So obviously that's it's definitely not a partial. So yeah, that's also a good help. Yeah.
Any other questions? Okay. Thank Richard again.